In this clip, I show a demonstration where they have current going through a wire, and it's inside a magnetic field, and it makes the wire jump. If you think about it, right, if you have current going through a wire and you have a magnetic field, you're going to have a force on it, just like you had with when you had one charge, right? You just have a bunch of charge now passing through. So the way that we do this, it's another right-hand rule, but very similar idea here. We have the force, and then current. This is the flow as positive charge, so we're going to use conventional current, and then B is the magnetic field, so FIB, and you can think of it as a fib, FIB. It's a fib, but it's true. Okay, FIB, force, current, field. And the way that we calculate this is multiplying the current times the length of the wire exposed to the field times the strength of the field. Current in amps, L is the length in meters, B is the magnetic field in Tesla, and the theta is the angle between the current and the field. If you think about it, QVB sine theta, right? You have a certain amount of charges, and they have a certain velocity, right? And if you multiply that velocity times a period of time, you're going to have a certain length x, right? So if you think about it, and we've got these values here, really V is just a displacement over time, right? So in other words, how far did these go? X in a period of time, and that's V, right? And so we know that Q over T, which is this portion here, the Q over T is current, so we multiply the current by the length of wire exposed, current going through and the length of wire exposed, and we can figure out the strength of the field. If you recall, N is the number of charges per unit volume, so the number of electrons per unit volume. A was the area in a wire, and then L is the length there, right? If you think about it, let's say you've got some particles in there, you have an electric field. The field is, let's say oriented like this, the magnetic field is, the electric field's like that. What's going to happen is, the electric field is going to have a force on the charge according to E equals force over Q, right? So E times Q is the force on it. So the force on the charge is QVB, and we know that as well. So we have the magnetic field force, and then we have the force due to the electric field as well. And if we have however many charges there, times the area times the length, every charge has a force on it, right? And so therefore, every single charge that you have in there is going to have a force on it according to the magnetic field that could be going through it, right? And so remember how we derived current in that unit, where we had N was the number of, was the number of charges per unit volume, A was the area, V was the velocity, and then Q is the, whatever charge. And we're using the elementary charge for these going through the wire. We could place these in here. And so what we end up getting, again, is ILB for that particular wire. And so it's important to be able to see that for this, that you'll be able to connect that idea of current, how we got current with that, and connect that to this idea here with the force on bunches of charges, right? That's what N is. It's, tons and tons and tons of charges, and over that length. And yeah, and we can get the force on that wire. So in this picture, we've got a wire that's hooked up to a cell or battery, and it's hooked up in two different ways. We have current passing through one way, current passing through the other way. And if you use the same right-hand rules, the force on these charges, or the force on the wires, makes sense based on the right-hand rule that we just looked at. And so, if you orient your hand with the one on the left, you're going to be pointing essentially into the screen. Your middle finger is going from north to south, and you'll see that your thumb is pointing down. If you orient your hand on the one on the right, you're going to be pointing basically at yourself. The current is pointing at you. Your middle finger is going from left to right, and your thumb is going to be pointing up. And so, just like we had with the first right-hand rule, with a single positive charge, now we're looking at conventional current, the flow of positive charge going through, and we can find out the force. All right, so in this one we have the current going from left to right. We have the field coming out of, or into the page rather. And I'm going to have you try this one. Go ahead and draw this on your sheet of paper and orient your hand and see if you can determine the direction of the force, and then we'll check. So go ahead and hit pause and give this a try. When you're ready to check, you can hit play to continue. Okay, so for this one, you should be pointing to your right. Your middle finger should be going towards your screen, and your thumb should be pointing towards the ceiling. And so this would be the force on this wire if there was a magnetic field, and that's the current going through. Let's try this one. Let's say the current is going into the page, and we have a magnetic field going from left to right, and we want to find the force on it. So go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. All right, so you should point your pointer finger into the screen. Your middle finger should be going to your right side, and your thumb should be pointing towards the floor. And that's what would happen to this wire if it was exposed to this field. So on this one, what is the force on a 100-meter long wire bearing 30 amps of current flowing north? If the wire is in a downward directed into the page magnetic field, 400 millitesla. So like this. So I'm going to have you go ahead and work this out. Calculate the strength of the force, and then also the direction of that force. And so go ahead and pause the clip and give that a try, and when you're ready to check, you can hit play to continue. Okay, so 1200 newtons to the left would be the force this would experience. And to orient your hand, you're going to be pointing towards the ceiling. Your middle finger is going into the page, into your screen here, and then your thumb should be pointing to the left. All right, so what is the magnetic field strength if the current in the wire is 15 amps and the force is directed downward towards the floor and has a magnitude of 40 newtons per meter? So I'll have you work through this one as well. You want to determine the direction of the current, as well as, in this one actually you're finding the magnetic field strength. We know the current, we want to find the direction of the current, and what the magnetic field strength is. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so the strength of the field is 2.67 Tesla. And the way that we can do this, it says that the force is 40 newtons per meter. So we could just consider a meter. Let's say this is a meter long, right? There would be 40 newtons on that. So that's what we could use for the length, and that's what we could use for the force. If it was 2 meters, we would have 80 newtons, and have that. So if we orient our hand, our middle finger is coming out of the page, our thumb is pointing down, and our pointer finger is going to the right. And so the current would be going to the right in this case. So, magnetic fields affect moving charges, individual charges, protons or electrons, as well as current. And we use that right-hand rule to determine the direction. And the key here is that it's moving, right? In both situations, with a single particle, you have a certain velocity. With I, current, you have a certain amount of coulombs per second, right, that are passing through. So let's take a look at this situation where we have a 5-meter long wire exposed to field that's 425 millitesla, and the current is 13 amps. So why don't you go ahead and try this one and calculate it and use the right hand rule to figure out the direction of the force, and when you're ready to check, you can hit play to continue. Okay, so we should have gotten 17.76 newtons, and if you think about it, the only component of this that is going to experience a force is the vertical component. And so that's why we're using sine of 40, because only the vertical component of the wire is going to experience a force. So if we orient our hand, in the direction that you can see with the vertical component, our, middle finger is going to the right, it's going to be into the page. The force will be into the page. So one of the powerful things that happened once the battery was created was, all sorts of experiments were able to be performed, and Ørsted was able to discover this, and it's kind of neat. There's a clip that I like to show in the video, E equals mc squared, where Faraday and his colleagues at the London Institute are replicating this, and seeing how when they put a compass around an electrical wire, that compass deflects. And before that time, they did not know that the magnetic, they knew about the magnetic field, based on the Earth's magnetic field, but they had no idea that electricity could create a magnetic field. And that's what they actually found, was that as electricity flows, it actually creates a magnetic field surrounding it. And this proved that electric current produces a magnetic field, this experiment itself. And they were dumbfounded. And Faraday, wasn't one of the premier scientists at the time. He was really just kind of an aide, but he eventually became, one of the most important scientists of all time, physicists of all time, with his discoveries. And he was able to think outside the box. He could picture, things actually, happening with fields, that were invisible. And, there's a very non-Newtonian, very, kind of outside of the box thinking. So the way that we know that the direction of the field coming around a wire is, this is another right-hand rule. And what I want you to do is to take your pencil and take the tip of your pencil and have that represent a wire that's continuing, and that's the direction of the current. So I want you to imagine that, the tip of that is the wire, the direction of the current is going upwards. Grab the pen or pencil with your right hand and have your thumb go in that same direction as the tip of your pencil. So when you do that, you can see that your fingers are wrapped around it, right? And so what this means is, around a current flowing wire, the current is going, through the wire, and your fingers are representing the direction of the magnetic field surrounding the wire. And as you go further and further out from the wire, the magnetic field is less and less and less. And so this is a pretty straightforward right-hand rule. You just grab the wire in that direction, and you've got that. So this is the list of instructions to do that. You can draw the current flowing. Place your thumb in the direction of the current, and then your fingers represent the magnetic field that surrounds the current carrying wire. And so if we draw that out, this is trying to draw something three-dimensionally here. Let's say, we've got that. The field is doing something like this. It's going into the page on the right-hand side, out of the page on the left-hand side. In front of the wire, it's going to the right. Behind the wire, it's going to the left. And, it loops around like that. And so, so hopefully you can picture that. We'll get a little bit of practice here with that too. Okay, so here's a wire with current going up, and you know, the field would look something like this. So, you know, the coming around the front, you know, around the back, and this may help, you know, visualize it a little bit. What I want you to do is go ahead and draw a wire with a dot, and so this represents the current coming out of the page. So I is coming out of the page. Remember, dots represent out of the page or out of the screen here. So what I want you to do is to take your pencil and grab it with your right hand, put your thumb at the tip of your pencil or pen, and point it at your face, just like the screen, you know, has the wire coming at you. So if you look at your fingers, right, look at your fingers, how they're wrapped around the wire. That's how the magnetic field is. So what I want you to do is to draw around this wire, draw what the magnetic field looks like, and we'll make sure that you got that. So go ahead and pause the clip and give that a try, and when you're ready to check, you can hit play to continue. Okay, so it should look like this, right? Your fingers are wrapped around it going counterclockwise, and that's the direction of the field. Now, if you notice closer to the wire, the field is stronger. The further you get away from the wire, the field gets weaker. So why don't you try this one now? Go ahead and draw a wire with the current going into the page, and orient your pen with your right hand holding it, and go ahead and draw what the magnetic field would look like in this case. All right, so it should look something like this. You know, your pencil should be going into the screen, your thumb is pointing into the screen, and your fingers are wrapped around it and going in a clockwise manner. This clip from MIT shows two parallel wires next to each other and current passing through, and they actually force on each other. I encourage you to look this up on YouTube to see that. So now we're going to talk about what happens with two wires and how they're forced with each other. The lab that we do in class, you know, gives practice to getting the intuition with this, so it'll be important to do that if you missed this lesson. But if the current is going in the same direction, those wires are going to be forced together. If they're going the opposite direction, then those two wires will be forced apart. The reason this is because each wire is creating a magnetic field, and then the other wire has current, right? So, you know, this wire right here, I2, has current going this way, and, you know, you could take your right hand rule and wrap your fingers around it, and this is going to create, you know, a magnetic field surrounding it like this, right? Going in a loop around like this. And so, including when it hits over here. And then we'll try to draw that. So when it hits here, right, it's going to be coming out of the page. And so if you do the other right hand rule, the FIB, you know, you're pointing to the ceiling, your middle finger's coming at your face, and then you'll see that your thumb is going to the right. And so, you know, and likewise, the other wire 1 is going to be producing a field that's going to hit the other wire and then force it as well. Page. So with the SI units, it's important to know the SI units and know what the fundamental units are. You know, we've talked about all of these, the meter, the kilogram, the second, Kelvin for temperature, mole for, you know, amount of mass that we have in a gas. And candela, you know, we actually use lux, or going to use lux as we go in the future with look into this, but candela is the SI unit. And the amp, it turns out, the ampere, is the unit of electric current. It's defined as the current which, when flowing in two parallel conductors 1 meter apart, produces a force of 2 × 7 newtons on a length of 1 meter. Now, why in the world did they, you know, establish the ampere this way? Well, you remember with the meter, right? We said, okay, you know, with the meter, this is, you know, we have a laser light, and how much time does it take for that laser light to go a meter? That's kind of nice, right? You know, that's a relatively modern thing that prevents us from having to have like a physical, you know, object. Now with the kilogram, you know, le grand que is still the official kilogram. and it's locked in a vault, right? And there's copies of it. They're still trying to figure out a way to make, a non-physical object for, the SI unit of mass. And then we have the second. Now, we've talked about that too. That's the transition of a hyperfine level of an electron and energy levels going back and forth. What they did with the ampere, it's very, very hard. If we look at current is how much Q over T, right? How much charge in a period of time. It's very, very hard to measure charge. We can do it now, but back then there's no way. They can measure charge very easily. And so what they did is they established this, whereas they said, if we have two parallel conductors, we actually have two wires, and we have current going through them, and they experience this much force, as they affect each other, because we have two wires, and they're producing magnetic fields. They're going to force on each other, and 1 meter is exposed. We're going to define that as an amp, and then we can work our way backwards actually for the Coulomb. And so, yeah, and that turned out to be a really helpful way to establish that SI unit. So again, why is the amp not based on the Coulomb? Like a Coulomb per second or something. Again, it was very difficult to measure, charge, and so it's much easier to measure force on wires. And if you send a certain amount of electricity through them, they could physically measure that force, and so that was very helpful. So in terms of the SI base units, the Coulomb then is the equivalent of 1 amp second or ampere second. So we have current is equal to Q over T, right? So if we cross multiply current times time, that's going to equal this. So let's say, you have 1 Coulomb in 1 second that passes by, that's going to be 1 amp. And that's what a Coulomb is a 1 amp second. All right, so here is a conducting wire, and we have current that's going around based on that black arrow there. And this is trying to show this three-dimensionally. The wire is coming out of the page and then into the page. And what happens is with this is if current's passing like that, and you grab that wire with your right hand, and we do this in class, probably the best thing that you could do if you can, if you want to grab like a roll of masking tape, this could be really good. And then you could just hold it like on like you see on the screen. So if you hold the masking tape, and feel free to pause the clip and grab one. This will help you with definitely help you with the visual here. If you grab the masking tape and you grab it with your right hand, and your thumb is pointing in the right hand direction, you'll see how your fingers pass through the middle, and those are representing those blue arrows passing through the middle and then coming around. And that's actually what happens with a magnetic field inside a current conducting wire, and that's in a loop here. And so that's that orientation. And outside of the wire, it's going the other way. But the blue lines, the blue dots here represent that the field going through the middle here. So this may be easier as well. You have this wire that you can see on the right hand side. The field is coming out of the page. If you take your piece of tape and grab the bottom of it, you'll see your finger coming at your face, and your thumb is going to the right. And you can move your hand all the way around the direction of the current, and you'll see that your fingers are still coming out of the page. And so hopefully you can visualize that okay. So what a solenoid is when you have a wire, and just like we just saw there, and you have current going through it, and this solenoid will produce a magnetic field. You may have heard of the term electromagnet, and that's exactly what happens. You have electricity going through a wire, and that creates a magnetic field. And so you don't actually have a permanent magnet, like an iron magnet, but you have this wire with the current passing through, and the magnetic field is produced there. Air core solenoids have nothing inside of them. Iron core solenoids are filled with iron, and so you have a wire that's wrapped around. So if you have that, right, if you have, let's say, like an iron nail like this, and you wrap it with wire, and you put some current through it, so this is the positive side, this is the negative side, current's going like this, and as current goes, it's going to wrap around, right, and you're going to create a magnetic field. This will actually create a magnetic field going north like this, and this will look just like a bar magnet, and it can act just like a bar magnet. And in fact, a lot of times whenever you see the use of magnetic fields, a lot of times they're used like that, where you have your your iron core or whatever it is, or even just wires, and it's creating that magnetic field.